Hello, Internet civilians, and today we're not going to talk about normal physics. Actually, we'll be talking about something much more complicated, quantum mechanics. So if you're one of the viewers who are still studying normal motion, forces, momentum, and such, you should probably skip this video and move on to the next one, unless of course you love to have your mind blown and being utterly confused. With that aside, let's start off with a little exercise to start you off. This exercise will get you to start thinking like a quantum physicist. I got this exercise from the E.04 ECW quantum mechanics course, so don't worry, it will be interesting. So, say that electrons have two properties, color and hardness, and we can separate the different kinds with the color and hardness sorting box. Out of the color box will be white and black electrons, while from the hardness box will be hard and soft electrons. No properties are in between. In this case, color and hardness are binary properties. Now, if I send the electrons through the color box, and then the white electron output through the hardness box, and the soft electron output back into another color box, what is the chance of the electrons from the second color box to be white? Well, according to your intuition and common sense, all the fine electrons should be 100% white, right? I mean, all the black electrons got sorted out in that first box. Wrong! 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 The percentage of the white electrons and black electrons is actually 50-50. And here I was, sitting at my desk, sipping strawberry yogurt, when this revelation came to me while watching the MIT course video. And I thought, what the heck, doesn't make any sense. There must have been something wrong with the experiment, right? These boxes must be faulty, something must have been wrong. But this experiment was conducted multiple times by professional experimentalists, and the same results appeared again and again, 50-50. This experiment is determined by the uncertainty principle of Heisenberg. Notice that's called the uncertainty principle. That the more you know about a particle, the less you know about its position and momentum. So basically it states that because of these properties you know about electrons, you will know less about its position in space, and that is just mind-blowing. With that taste of what quantum physics is about, let's get into some history. Near the end of the 19th century, with Newtonian laws of motion and James Clerk Maxwell's explanation of electric charge and magnetic forces, physicists believed they were nearing the end of physics and that all of the universe would be explained soon. Oh, but they were so wrong. An experiment in the early 1900s called the black-body radiation experiment was conducted by physicists Lord Rayleigh and J.H. Jeans. The experiment consisted of a material called black body, which could absorb and release electromagnetic radiation. They decided to make an oven out of the material, and to study the frequency and the radiation that came out of the oven while changing the heat of the oven. What classical physics would say is that infinitely small amounts of energy would be continuously added to the system while the frequency is increased, that there would be no fundamental amount of energy. This holds true with all classical physics, that matter and energy are continuous, and that there is no fundamental state of either. The data of the experiment showed a curve in the lowest frequencies, similar to Rayleigh and Jeans' predictions, but when it got to higher frequencies such as ultraviolet light, the graph started to diverge. This was called the ultraviolet catastrophe. People have conducted the same experiment over and over, and the results are the same, so it wasn't the experiment that was conducted incorrectly. So Rayleigh and Jeans' law, which was based entirely on classical physics, was actually wrong. Max Planck proved this by unintentionally making his own equation for the situation. E is equal to hf. He suggests that energy was distributed in packets he called quanta. Each quanta was directly correlated to a constant that was later named Planck's constant. This was absolutely crazy for physicists at the end of the era, and many refused to recognize Planck's quantum theory as legitimate. One of the only people who really believed Planck was a young German named Albert Einstein, and he was about to change everything. So where are we at on the timeline? Let's see. Newton discovers gravity and established most of classical physics. Maxwell discovers an electromagnetic force. Planck overturns classical physics and he gets bullied for being absurd. What happens next? Albert Einstein, whose name should ring a bell, was a patent clerk before he became a world-renowned theoretical physicist. He saw these patents for new scientific theories and was intrigued by them. Because he could finish his work early, he had a lot of time to think and wonder about the universe. This eventually led to the publishing of his first paper in 1905. He wrote about many things, including the photoelectric effect and the special theory of relativity. The photoelectric effect is the observation that when electromagnetic radiation hits a metal, that it would give off electrons that physicists would refer to as photoelectrons. Einstein pointed out that the results of the experiment connect directly to Planck's equation, E is equal to hf. He simply rearranged it to fit the problem. The maximum kinetic energy is equal to h times f minus f sub 0. This would prove that Planck's ideas were true, and that energy was quantized in packets. Not only did Einstein prove quantization, but he proved the existence of photons, the particles that make up electromagnetic waves. He proved this by stating that only particles with momentum could have knocked off the electrons from a metal. However, light was still somehow a wave and a stream of particles at the same time. This was later called wave-particle duality, and all elementary and quantum particles also behave as waves. Another experiment supported the idea of wave-particle duality was the two-slit experiment. Thomas Young conducted this famous experiment in 1801, and what he did was that he shined light through two small slits onto black film. When he did so, the light ended up creating an interference pattern, where the two crests of the wave met would be where more of the light ended up, while the intersecting troughs formed a deconstructive pattern where there was almost no light. This experiment proved that light was a wave, but when taken into account along with the photoelectric effect, one can say with certainty, and not uncertainty, that photons and other elementary particles follow the rule of wave-particle duality. People began to believe, Planck and Einstein, that quantum theory is the truth of the microscopic world. However, there were still many who did not agree with their discoveries. Meanwhile, a British physicist named Ernest Rutherford and his colleagues got together to test one of the most controversial experiments in the history of science, the gold foil experiment. They basically set up just a really thin layer of gold foil and shot a bunch of alpha particles at it. Once the alpha decay simply went through the foil like it should have, but a decent amount bounced back or were thrown off at an angle. Before this experiment was done, the idea of an atom looked like this. However, when the data for this experiment came out, another physicist named Niels Bohr successfully made a diagram of the atom. Now that I think about it, the new diagram looks kind of boring. I'm so sorry. Let's get back onto the timeline. Let's see. Rutherford finds enough evidence to prove the existence of protons. Happy 1920. James Chadwick and E.S. Bueller conclude that some kind of strong force holds the atom all together. And at this time, from Einstein's general theory of relativity to 1926, nothing really quite new or thought-provoking happened. It was mostly just confirmations of antecedent theories. In 1926, an Austrian physicist named Erwin Schrödinger came up with an equation for the wave-like behavior of certain fundamental particles called bosons, and he called it Schrödinger's equation. Really creative, Schrödinger. At the same year, another German physicist named Max Born described quantum mechanics with probability functions. And to end off the year, G. N. Lewis names the photon. Great job, Lewis. A for effort. In 1927, Heisenberg, remember this guy? Came up with the uncertainty principle. And if you don't remember, it was the more you know about a particle's energy, the less you know about the other characteristics of that particle, such as momentum and location. Now, in 1928, a man named Paul Dirac was able to describe an electron with the equations he made from his knowledge of quantum mechanics and special relativity. And to finish off the beginning, by 1930, almost all of theoretical physicists believe in quantum theory and its parts. So there we go. We now have our completed timeline. In 30 amazing and productive years, the world was able to come together to discover and learn so much about the universe around us. I can't tell which is more impressive, the actual quantum theory or the great people who had the intellect to make it happen. But the true beauty of quantum physics lies in this. It never ends. Today's theoretical physicists are working hard at it to find out more and more about space-time and its strange and unlimited mysteriousness. They're even in the process of creating the world's first quantum computer, a computer that has exponentially increased efficiency with the power of quantum physics. Space and time will allow us to keep imagining and theorizing and formulating all about our vast and boundless universe, but as only as long as we are willing to do so. First of all, I would love to thank Khanacademy for showing me this great opportunity to learn about things I never knew about before. It's really been an enlightening experience for me, and I hope I can apply this knowledge again soon. Secondly, I would like to thank all the sites I used. I put all of them in the description, so don't worry. And lastly, I'm thankful for my teachers, my friends, and my family for being supportive. And all thanks aside, thanks for watching, and I'll see you all in the next video. They're even in the process of creating the world's first quantum computer, a computer that has